In part 2 of the lecture on electromagnetism, I will discuss the interaction between charged particles and magnetic fields, transformers, and electromagnetic waves. Placing a wire that carries no current in magnetic field results in no motion of the wire. The wire does not interact with the magnetic field. Remember that a standard conducting wire is made from copper, and copper is non-magnetic material. So that explains why there is no interaction between the wire and the magnetic field. However, if a current is running through the wire, then the wire interacts with the magnetic field and it experiences a force that moves it in space. So a current-carrying wire placed in a magnetic field will experience force which is perpendicular to the magnetic field and the direction of the current. So here is a current-carrying wire, and the direction of the current in the wire is indicated by these green arrows. This wire is placed in magnetic field B, which is directed like so. And the wire is going to experience force because of the interaction between the current and the magnetic field that will be perpendicular to both the current and the field, and that force will be directed vertically up in this particular example. Notice that in this setup, the current is perpendicular to the magnetic field, and the force that the wire experiences is also perpendicular to the current and to the magnetic field. The direction of the resultant force here that the wire experiences is determined by the right-hand rule, where we place the fingers of our right hand along the direction of the current in the wire. The thumb of the right hand points in the direction of the magnetic field, and then the resultant force is coming out of the palm of the hand. So why does the wire that carries current interact with the magnetic field? The electric current is a collection of charges flowing in one direction. So this means that charged particles will experience magnetic force when moving in a magnetic field. If the particle is moving parallel to the field, no force will act on it. But if the particle is moving perpendicular to the field, it will experience force. And so in this example here, the moving particles are electrons, and that is the electric current. They're moving perpendicular to the magnetic field lines, and so therefore they will experience a force due to the interaction with the magnetic field. When all the particles moving in the wire, the forces that act on them are combined, that results in a force large enough to actually move the entire wire inside this magnetic field. When a single particle enters magnetic field, as shown in this drawing, the magnetic field is directed vertically up. The particle enters the field with velocity indicated by this orange arrow. The interaction with the field will make the particle go around a circle, and the motion will be uniform circular motion, which means it's motion without acceleration. From before, we know that when we have motion without acceleration, the object in motion is under the action of a centripetal force. And so this is the force that acts on the charge due to the interaction with the magnetic field. This force points towards the center of the trajectory of the charge. Another possibility is that the velocity of the charged particle is not perpendicular to the magnetic field, but it has components, one perpendicular and one in the direction of the magnetic field, in which case the particle will move around this helical trajectory. So that is a combination of circular motion plus linear motion. the motion of the Earth around the Sun as the Sun is moving through space actually looks like this over time. Let's go back to the first drawing here. This effect, where a particle enters the magnetic field at a direction perpendicular to the field, is used in current particle accelerators, where charged particles, electrons or protons or other, are passed through a magnetic field which causes them to go around the circular path. And so such particle going around the circular path multiple times will accelerate as it goes because of the changing magnetic field inside the accelerator. And typically, two beams of particles are generated that are moving in opposite directions. And when certain levels of energy of the beams are achieved, the two beams are collided with each other, and then scientists study the formation of exotic elements or even new elements. For example, some of the most recent elements in the periodic table, which are extremely heavy, are artificially created in particle accelerators. Now let's see how do we calculate the magnetic force that a particle experiences inside a magnetic field. The magnetic force is calculated as the product of the charge of the particle, the speed of the particle, and the magnitude of the magnetic field. Here we always assume that the particle is moving perpendicular to the magnetic field and not like the second drawing is showing. The calculation of the force here is obviously much more simple given the formula that's presented here compared to the second case. So we are not going to deal with that case. Since the motion of a charged particle in magnetic field is uniform circular motion, as I mentioned before, this particle is under the action of magnetic force, which is the centripetal force for that motion. So here is my setup. This is my charged particle, and this charged particle is in a magnetic field that points down, like so, and so the particle goes around the circular trajectory, like so, with speed v, and centripetal force F that points towards the center of the trajectory. So the centripetal force from before, we know, is equal to the mass of the particle times the centripetal acceleration. We also know from before that the centripetal acceleration is related to the speed of the particle and the radius of this circular trajectory. And so replacing the centripetal acceleration with its expression in terms of velocity and radius, we get that the centripetal force is equal to the mass of the particle times the speed of the particle to the second power divided by the radius of the trajectory. However, we also know that the magnetic force, which is the centripetal force, is equal to the charge of the particle times the speed of the particle times the magnetic field magnitude. So those two expressions for the centripetal force can be used in combination to solve various problems about charged particles moving in magnetic fields. Let's do some examples. First example, I want to convert 25 Tesla to Gauss. Tesla and Gauss are units for magnetic fields, and Tesla is the unit in the metric system. We know that 1 Tesla is equal to 10,000 Gauss, so therefore 25 Tesla will be equal to 25 times 10,000 Gauss, well, that is 25,000 Gauss. Here's another example. An electron has velocity of 4 times 10 to the 6th meters per second, which is perpendicular to a 2 Tesla magnetic field. What force and acceleration does the electron experience? Since this is a problem about the force that a charged particle experiences in magnetic field, to find the force, I'm going to use the formula that I discussed on the previous slide, and that is that the force is equal to the charge of the particle times the speed of the particle times the magnitude of the magnetic field. So substituting the values provided in the problem and remembering that the charge of the electron is 1.6 times 10 to the negative coulombs, I get 1.6 times 10 to the negative 19 coulombs times 4 times 10 to the 6th meters per second times 2 Tesla. That is equal to 1.28 times 10 to the negative 12 newtons. Now I also want to find the acceleration with which the electron is moving. Since the electron is going to be moving along a circular trajectory, like so, that means that there is centripetal force and centripetal acceleration acting on the electron. We already know the centripetal force is the magnetic force, but the centripetal acceleration is also directed towards the center. Let's draw it right here. So we want to find the centripetal acceleration. To find the centripetal acceleration, I'm going to simply use Newton's second law that says the centripetal force is equal to mass times centripetal acceleration. From here, the centripetal acceleration is simply the force divided by the mass. The force we already found, that is 1.28 times 10 to the negative 12 newtons. The mass of the electron is a table constant, and it's equal to 9.11 times 10 to the negative 31 kilograms. So the acceleration with which the electron is moving is equal to 1.28 times 10 to the negative 12 newtons divided by 9.11 times 10 to the negative 31 kilograms. When you calculate that, you should get 1.41 times 10 to the 18th meters per second squared. The relationship between current and magnetism is used in various applications, one of which is stepping down or stepping up the voltage in an AC circuit. An AC circuit is, for example, the power grid that everybody uses to plug in their appliances at their house. Why do we need a device that can step up or step down voltage? Well, for example, from the outlet in your house, you're getting 120 volts, but let's say your phone charges with a charger that only operates at 9 volts. So that means that if you plug your cell phone directly to the outlet, you're going to burn it out. So your charger brick contains a small device that steps down the voltage from the outlet to the desired 9 volts. Similar thing happens when the power plant produces electricity. So at the exit of the power plant, there are millions of volts of electricity produced. Obviously, that is absolutely not useful for our needs at home or even industrially. And so there is a need for stepping down the voltage. And so along the way of the power lines, there are transformer relays that step down the voltage to the desired 120 volts that reaches our homes. And so a device that can step down or step up the voltage produced by a certain power source is called a transformer. A transformer consists of a core made from iron or nickel and 2 sets of coils. So here is a drawing of a transformer. So we have a core that is made from iron or nickel and 2 sets of coils. One coil is named the primary coil and the other coil is named the secondary coil. So this is the primary coil, this is the secondary coil. The primary coil has Np number of turns, and the potential difference between the two ends of the coil is Vp. The secondary coil has Ns number of turns, and the potential difference between the two ends of the coil is Vs. So one more time, Np is the number of turns of the primary coil, and S is the number of turns of the secondary coil. Vp is the voltage at the primary coil, Vs is the voltage at the secondary coil. And so, depending on the number of turns on each coil, the output voltage at the secondary coil will be either higher than the voltage at the primary coil or lower. When the number of turns of the secondary coil is smaller than the number of turns at the primary coil, the secondary voltage is smaller than the primary voltage. When the roles are reversed, meaning the secondary coil has more turns than the primary coil, then the secondary voltage will be higher than the primary voltage. So the first configuration is an example of step-down transformer. The second configuration is an example of a step-up transformer. So what is the relationship between the parameters of a transformer? The number of turns of the primary and secondary coils and the voltages at the primary and secondary coils. This is the relationship. The ratio of the number of turns of the secondary coil to the number of turns of the primary coil is equal to the ratio of the voltage at the secondary coil to the voltage at the primary coil. Let's do the following example involving transformers. A transformer is used to convert 120 volts electricity to 9 volts to use for a portable radio. The primary coil of the transformer has 600 turns. How many turns does the secondary coil have? Here we use the relationship that I discussed on the previous page, and since I'm looking for the number of turns of the secondary coil, that means that I must rearrange the terms here to get an expression for the number of turns of the secondary coil. So Ns is equal to Vs times Np divided by Vp. Now I'm ready to substitute the values in this expression. So Ns is equal to 9 volts times 600 turns divided by 120 volts. The units of volts cancel out, and then the result is that Ns is equal to 45 turns. We know that electric charges produce electric field. We also know that moving charges, which make electric currents, produce magnetic fields. So then that means that moving charges simultaneously produce magnetic and electric fields. And so moving charges produce magnetic and electric fields that propagate away from those charges. And the combination of the two fields propagating together in space is called an electromagnetic wave. So that means that any charged particle that is moving in space produces electromagnetic waves. The directions of oscillations, or in other words, the polarization of the fields, are perpendicular to each other. This is shown in this drawing of an electromagnetic wave. So we have a combination of magnetic and electric fields. The electric field is presented with red, and the direction of polarization here, or the direction of oscillation, is vertical to the direction of propagation. The magnetic field is presented with purple, and the polarization of the magnetic field, or the direction of oscillation, is perpendicular to the direction of propagation of the wave, but horizontal. So the electric field is perpendicular to the direction of propagation vertically, and the magnetic field is perpendicular to the direction of propagation horizontally. So the two fields are perpendicular to each other. And as you can see, as the electric field oscillates, so does the magnetic field. And so the two fields combine and propagate together in that direction in this particular example, and the combination of the two fields is the electromagnetic wave. Again, those two fields were generated by some moving charged particle. Electromagnetic waves are moving with the speed of light in vacuum. The electromagnetic spectrum is shown below, and this is a very large range that encompasses frequencies from 10 to the 22nd all the way down to the hundreds, and wavelengths from 10 to the negative 14th all the way up to the hundreds of meters. And so here, schematically, is shown the various types of electromagnetic waves. Starting with the highest frequency, we have gamma rays. Then we have X-rays. After X-rays, we have UV. The visible range of electromagnetic radiation is shown with this white strip right here. Then after that, we have infrared, we have microwaves, and then finally we have radio waves. So no matter what type of electromagnetic wave we are discussing, remember that the speed of those waves is equal to the speed of light in vacuum, 3 times 10 to the 8 meters per second. And so, since this is an example of a wave phenomenon, the relationship that we've seen many times before between speed, wavelength, and frequency applies here as well. So the speed is equal to the wavelength times the frequency, where the speed is equal to the speed of light is equal to 3 times 10 to the 8th meters per second. With this, I'm going to conclude the lecture on electromagnetism.